In the previous chapter, we encountered the Fourier series representation of a periodic function in a fixed interval as a superposition of sinusoidal functions. It is often desirable, however, to obtain such a representation even for functions defined over an infinite interval and with no particular periodicity. Such a representation is called your Fourier transform and is one of a class of representations called your integral transforms. In this lesson, we begin by considering Fourier transforms as a generalization of Fourier series. We then go to discuss the properties of the Fourier transform and its applications. The Fourier transform provides a representation of functions defined over an infinite interval and having no particular periodicity in terms of a superposition of sinusoidal functions. It may thus be considered as a generalization of the Fourier series representation of periodic functions. Since Fourier transforms are often used to represent time-varying functions, we shall present much of our discussion in terms of f of t rather than your f of x. Later you'll see that most of our examples will have your f of t, which is far from your f of x, which we have used in our previous lesson on your Fourier series. Although in some spatial examples, f of x will be more natural notation, and we shall use it as appropriate. Our only requirement on f of t will be that the integral of the modulus of f of t dt is infinite from negative infinity to positive infinity. In order to develop the transition from Fourier series to Fourier transforms, we first recall that a function of period t may be represented as a complex Fourier series. So this is what we did in our last video, where we represented your Fourier series into a complex Fourier series. And your complex Fourier series is your f of t is equal to the sum of your c sub r e 2 pi irt over t, where your big T is your period. And we can also write this one as the sum of your c sub r e exponential I omega r t, where here your omega r is equal to 2 pi r over t. As the period t tends to infinity, the frequency quantum, your delta omega, which is equal to 2 pi over t, becomes vanishingly small, and the spectrum of the allowed frequencies of your omega r becomes a continuum. The infinite sum of terms in the Fourier series becomes an integral, and the coefficients c sub r become functions of the continuous variable omega as follows. We recall that the coefficients of c sub r in 13.1 are given by your c sub r is equal to 1 over t times the integral of f of t e negative 2 pi I r t over t dt integrated from negative t over 2 to t over 2. This can be rewritten as equal to delta omega over 2 pi times the integral of f of t e negative I omega r t dt from negative t over 2 to t2, where here we have the integral in two alternative forms, and for convenience made one period run from negative t over 2 to positive t over 2 rather than from 0 to t. Substituting from equation 13.2 into 13.1 gives us this expression for your f of t. So you have the sum of delta w over 2 pi times the integral of f of u. So we just use here your u, e negative I omega ru du e negative omega rt. So we just change from u in order for us to not be confused. And just at this stage, your omega r is still a discrete function of r equal to 2 pi r over t. Now look at this figure here. As you can see, you have your solid lines, and then you also have here your broken lines. So this shows us the relationship between the Fourier terms for a function of period t and the Fourier integral, which is the area below the solid line of the function. Now the solid points are a plot of the real part of your c sub r e I omega rt as a function of r, or equivalently of omega r. Your 2 pi over t times c sub r e exponential I omega rt gives the area of the arc broken light rectangle. So remember that you're going uh, to get the integral of this function here, that is just equal to the area under the curve here. Now, if t, your period t, tends to approach infinity, then your delta w, which is equal to 2 pi over t, becomes infinitesimal, and the width of the rectangle tends to 0. So if the period t tends to infinity, these rectangles here become smaller and smaller. The width of this rectangle becomes smaller and smaller, and it tends to approach to 0. From the mathematical definition of an integral, you have the sum of your delta omega over 2 pi times g of omega r e I omega rt. This is just equal to 1 over 2 pi integral of g of omega e I omega t dw. And this definition is just your Riemann sum integral, where if you're going to take the limit of this summation here, you get the integral of the same function. And in this particular case, your g of omega r is equal to the integral of f of u e negative I omega ru du evaluated from negative t over 2 to positive t over 2. From that, your equation 13.3 becomes your f of t is equal to 1 over 2 pi integral of dw e I omega t times the integral of du fu e I omega u. And this one here is known as your Fourier's inversion theorem. So equation 13.4 is your Fourier inversion theorem. From it, we may define the Fourier transform of f of t. So if you're going to refer to the Fourier transform of f of t, you're going to write it in this term. So the Fourier transform of f of t is your f with this line here, with this wavy line, f of omega. So if you see this symbol here, this is what you're referring to as the transform of your f of t. So the Fourier transform of f of t is equal to 1 over 1 over the square root of 2 pi times integral of f of t e negative I omega t dt. And the inverse of this Fourier transform is your f of t that's equal to 1 over square root of 2 pi integral of your f, how do you call this? F per omega e I omega t dw. So the inverse of this one is just this one, and the inverse of this equation is this equation here. Remember again here that this is your Fourier transform of your function f of t. And from your Fourier transform, you can get your f of t by using this equation here. So take note of equation 13.5 and 13.6, as these are the equations that we're going to use later in our in our examples. For example, let's find the Fourier transform of the exponential decay function f of t, which is equal to 0 for t less than 0, and f of t equal to a exponential negative lambda t for t greater than or equal to 0, or lambda is greater than 0. So our task here is to find for the Fourier transform of the exponential decay function, which are set by conditions here. And we are going to use, again, equation 13.5, your Fourier transform of f of t, which is, again, this one here. Your Fourier transform is equal to 1 over square root of 2 pi times the integral of f of t e negative I omega t dt, evaluated from negative infinity to positive infinity. And as you can see here, we have two conditions. So your f of t is equal to 0 for t is less than 0, and f of t is equal to a exponential negative lambda t for t that's greater than or equal to 0. So we're going to separate the integral into two parts. One is the integral from negative infinity to 0 for f of t that's equal to 0, and the other one is the integral from 0 to positive infinity, or your f of t that's equal to a exponential negative lambda t. So this is your integral here. Your Fourier transform is equal to 1 over square root of 2 pi times the integral of 0, because again, this one, 0 for t that's less than 0, e exponential negative I omega t dt, plus your 1 over square root of 2 pi integral of a exponential negative lambda t e I omega t dt, where we can just take out your a out of the integral because this is just a constant. And take note here that the first term is evaluated from negative infinity to 0. The other half is integrated from 0 to positive infinity. And as you can see, this term here is just 0. So we're just going to evaluate this term here. We can simplify this one so that your exponential terms can be combined to your exponential negative lambda t minus I omega t, or you have your exponential negative lambda t plus I omega t. You can also take out your t out of the equation because your t is what we're going to integrate. So you already know how to integrate this one. So the integral of this function here is your that's a over square root of 2 pi times negative e uh, exponential negative lambda plus I omega t over lambda plus I omega. This is evaluated again from 0 to positive infinity. Evaluating. So your Fourier transform is equal to a over square root of 2 pi times lambda plus I omega, which is the required transform. And it is clear that the multiplicative constant a does not affect the form of the transform, merely its amplitude. This transform may be verified by the substitution of the above result into equation 13.6, or the inverse of your Fourier transform. And from that, you should recover your f of t. But evaluation with integral requires the use of complex variable contour integration, which is out of this topic. An important function that appears in many areas of physical science, either precisely or as approximation to physical situation, is the Gaussian or your normal distribution. I hope that you have already encountered this one in your previous statistics and probability classes. Its Fourier transform is of importance both in itself and also because When interpreted statistically, it readily illustrates a form of your uncertainty principle, and your uncertainty principle is commonly applied in your quantum mechanics. So let's talk a little here about your uncertainty principle from your Gaussian distribution, where um, applying the Fourier transform in your Gaussian distribution, we see the we see some forms of your uncertainty principle. Now let's start with the normalized Gaussian distribution. So this one here is your normalized Gaussian distribution. It's equal to your f of t is equal to 1 over tau squared root of 2 pi exponential of negative t squared over 2 tau squared. This is defined from negative infinity less than t less than positive infinity. So again, this one here is your normalized Gaussian distribution. I hope that you have seen this one in previous probability classes. And what you're going to do here is to find the Fourier transform of this normalized Gaussian distribution. Again, from the equation for your Fourier transform, your Fourier transform is equal to 1 over square root of 2 pi times the integral of f of t e or exponential I omega t dt. This is evaluated from negative infinity to positive infinity. So we're just going to substitute your f of t to your Fourier transform equation here. The Fourier transform of f of t is then given by your 1 over square root of 2 pi integral of 1 over tau square root of 2 pi exponential negative t squared over 2 tau squared exponential negative I omega t dt. So we just use this equation and then substituted your f of t or your normalized Gaussian distribution in this equation here. So we have again here your Fourier transform already substituted with your normalized Gaussian distribution, but we still need to simplify this one. But before that, as you can see here, we have two exponential terms. You have exponential negative t squared over 2 tau squared and exponential negative I omega t. We can actually combine these two so that we have this form here. You have your exponential negative t squared over 2 tau squared minus I omega t. And we can actually have this form here where, as you can observe, we did some completing the square where the quantity negative tau squared I omega squared over 2 tau squared has been both added and subtracted in the exponent in order to allow the factors involving the variable of integration t to be expressed as a complete square. So what we did here was we had a completing of square. So just going back one step up, what we have is you have your exponential of negative t squared over 2 tau squared minus I omega t. So we added negative tau squared I omega squared over 2 tau squared, and we also subtracted the same function. So you have this one becomes negative. So plus, or this is minus, and then we have subtracted also the same term. So you have minus the negative, so that's plus tau squared I omega squared over 2 tau squared. So this is now your exponential, but as you can see here, this I omega t, let me erase this one. Let's erase this one. And your I omega t can actually be written as this one. So you have your t tau squared I omega t over 2 tau squared. So that all the terms in the expression, in the exponential expression, will have a fraction which is over 2 tau squared. So this is 2 tau squared over 2 tau squared over 2 tau squared over 2 tau squared. And if you have that one, you can take out your negative 1 over 2 tau squared, which is what we actually did here. Okay, and so we're just left with your t squared plus 2t squared I omega t plus your t squared I omega squared your minus your t squared I omega squared. So again, what we did here is we have your completing the square, and we take out your 1 over negative 1 over 2 t squared out of the exponential expression. So this is again the expression earlier, and we did the completing the square so that this expression here is just equal to your t squared plus I tau squared omega, and then this is squared. So if you're going to evaluate this one, you get this expression here. But we still have this negative tau squared I omega squared, which is we can just take out this one out of the equation, as this does not contain your t term. So you see this one here. This is just this term here taken out of the exponential expression, so that we are just left with your 1. We're just left with your 1 over your tau square root of 2 pi integral of exponential of your negative t plus I tau squared omega squared over t over 2 tau squared dt. So we're just going to um, evaluate this integral here, which is easier. Okay, and the quantity inside the braces is the normalization integral for the Gaussian and equals unity. So this one here, this is just actually equal to 1, the quantity inside the braces. Although if you want to show this one, you need to know about your complex variable theory, which is out of scope of this lesson. So this expression here is just actually equal to 1. This quantity is the normalization integral for the Gaussian and equals unity. So we're just left with the final result that since this is equal to 1, we are left with your Fourier transform is equal to 1 over 2 pi exponential negative tau squared omega squared over 2, which is, as you can see, just another Gaussian distribution centered on 0 and with a root mean square division of delta omega, which is equal to 1 over tau. It is interesting to note, and an important property, that the Fourier transform of the Gaussian is another Gaussian. So just a quick review. This one here is our normalized Gaussian distribution. This Gaussian distribution is centered on t equal to 0 and has a root mean squared division of delta t that's equal to tau. This one here is your Fourier transform, which is still another Gaussian distribution centered on 0. I mean, a root mean square deviation of delta w that's equal to 1 over tau. So from your normalized Gaussian distribution, we found the Fourier transform of your normalized Gaussian distribution here, which is still another Gaussian distribution. And in the above example, the root mean square derivation in t was tau, as you can see here. And so it is seen that deviations or spread in t and tau are just actually inversely related. That is, you have your delta omega times delta t is equal to 1. And this is independent of the value of tau. And this term here is actually now your expression of your uncertainty principle, which you will see more in quantum mechanics. Um, Again here, your delta omega times delta t is equal to 1 has the following meaning. In physical terms, the narrower in time is, say, an electrical impulse, the greater the spread of the frequency component it must contain so that it's equal to 1. Similar physical statements are valid for other pairs of Fourier-related variables such as your spatial position and the wave number. And in an obvious notation, you have your delta k, delta x is equal to 1 for a Gaussian wave packet. The uncertainty relations as usually expressed in quantum mechanics can be related to this if the de Broglie and Einstein relationships for momentum and energy are introduced, which is the following. You have your de Broglie relationship, your momentum is equal to h bar times k, and your Einstein relation, which is your energy that's equal to h bar omega, where here your h bar is your Planck's constant h divided by your 2 pi. In a quantum mechanics setting, f of t is a wave function and the distribution of the wave intensity in time is given by your modulus squared of f, which is also a Gaussian. Similarly, uh, the intensity is the intensity distribution in a frequency is given by the modulus squared of your Fourier transform. Now, these two distributions have respective root mean square deviations of tau over square root of 2 and 1 over square root of 2 tau, giving, after the incorporation of the above relations, we get the following. We have your delta E times delta T is equal to h bar over 2, and delta P over delta X is equal to h bar over 2. This one here are your uncertainty principles in your quantum mechanics, and you will learn more about this one when you go to that specific course. So this is specifically this one is the uncertainty in your momentum and then your position, which tells us that you cannot anywhere be certain with your momentum if you know the position, and you cannot anymore know you cannot be any more certain with your position if you know your momentum. So you learn more about this one when you go to quantum mechanics. Now let's talk about the Dirac delta function. The delta function is different from most functions encountered in the physical sciences, but we will see that a rigorous mathematical definition exists. It can be visualized as a very sharp, narrow pulse in space, time, density, etc., which produces an integrated effect having a definite magnitude. So this one here is an example of a Dirac delta function, which is sharp, narrow pulse in space, time, or density. So here this is in terms of space. The Dirac delta function is a property that uh, your your delta of t is equal to 0 for t that's not equal to 0. But its fundamental defining property is that the integral of f of t of delta t minus a dt is equal to f of a, provided that the range of integration for this integral here includes the point t that's equal to a. Otherwise, the integral equals 0. This leads immediately into further useful results. You have the integral of delta of t dt that's equal to 1 for all a and b that's greater than 0, and You have your integral of delta of t minus a dt that's equal to 1, provided that this integration here includes your t is equal to a in the range. Other useful properties of the Dirac delta function are the following. Your delta of t is equal to your delta of negative t. Your delta of at is equal to 1 over modulus of a, or the absolute value of a, times delta of t. And t times delta of t is equal to 0. Furthermore, by considering an integral of the form of this one here, the integral of f of t, uh, delta of h of t dt, and making a change of variables to z that's equal to h of t, we may show that your delta h of t is equal to the summation of your delta t minus ti over the modulus of h prime of ti, where your t sub I are those values of t for which your h of t is equal to 0, and h of t stands for your dh over dt. The derivative of the delta function del prime of t is given by this expression here. The integral of f of t del prime of t dt is equal to your f of t delta of t evaluated from negative infinity to infinity minus this term here, which is equal to the negative of uh, your f prime of 0. And this is similar for higher derivatives. Now, what's the relation of your Dirac delta function to Fourier transforms? In the previous section, we introduced the Dirac delta function as a way of representing very sharp narrow pulses, but in no way related it to the Fourier transform. We now show that the Dirac delta function can equally well be defined in a way that more naturally relates it to the Fourier transform. Referring back to the Fourier inversion theorem in equation 13.4, which is this one here, we have f of t that's equal to 1 over 2 pi times the integral of this term here, your d omega ei omega t times integral du f u ei omega u, wherein uh, we can rearrange so that you have this kind of form here. You have the integral of du f u times 1 over 2 pi of the integral of e exponential I omega t minus u du. So we just combine uh, your two exponentials and we have rewritten it in this term here. And you can compare this one with equation 13.12, which is this one here. So let's compare this expression here with equation 13.12. What do you see? You have your f of t, or we can match this one. This your f of t is, or your f of u is matched to your f of t. Your du is matched to your dt. So that means here that this term is matched to your delta of t minus a. It shows that we may write the delta function as the following. So your delta of t minus a, or t minus u, is equal to 1 over 2 pi times the integral of exponential I omega t minus u d omega, evaluated from negative infinity to positive infinity. So we have this term here. Considered as a Fourier transform, this representation shows that a very narrow time peak at t equals 0 results from the superposition of complete spectrum of harmonic waves and all frequencies having the same amplitude and always being in phase at t is equal to 0. So we have rewritten your Dirac delta function in terms of your Fourier transform. This suggests also that the Dirac delta function may be represented as the limit of the transform of a uniform distribution of unit height as the width of this distribution becomes infinite. For example, consider the rectangular distribution of frequencies shown here. So you have your Fourier transform of your omega, which is equal to 1. So from your equation 13.6, taking the inverse Fourier transform, this is your equation 13.6 here, and we take the inverse Fourier transform where your Fourier transform f omega is equal to 1. So you have your f omega t, the inverse of your Fourier transform is equal to 1 over square root of 2 pi times integral of 1 times e I omega t d omega evaluated from negative omega to positive omega. So you can just evaluate this one. As you can see, you just have your e I omega t d omega. So the integral of this function here is equal to your 2 omega over square root of 2 pi sine omega t over omega t. Now again, what we have here is the inverse of your Fourier transform f omega of t, which is equal to 2 omega over square root of 2 pi sine omega t over omega t. So as you can see here, this one is the Fourier transform, and this one is the inverse of the Fourier transform. This function, uh, uh, from this function, it is apparent that for large omega, it becomes very large at t is equal to 0, and also very narrow at t that's equal to 0. We also note that in the limit, as your omega approaches to infinity, your f omega of t as defined by inverse Fourier transform tends to 2 pi uh, 2 pi raised to the 1/2 of delta of t by virtue of your equation 13.24. We may conclude that the delta function can also be represented by the following here. Your delta function, delta of t, is equal to the limit of sine omega t over pi t as your omega approaches as your omega approaches to infinity. We also note that the Fourier transform definition of the delta function in 13.24 shows that the latter is real since your del star of t is equal to 1 over 2 pi times integral of e I omega t dw, which is equal to your del of negative t. But again, remember that your del of negative t is just equal to your delta of t. And finally, the Fourier transform of a delta function is just simply this one here. The Fourier transform of your delta function, delta omega, is equal to 1 over square root of 2 pi. So this is just the Fourier transform of your delta function, of your Dirac delta function. Now, lastly, let's discuss the properties of the Fourier transforms. Here we list these properties without proof. They can be verified by working from the definition of the transform. As previously, we denote the Fourier transform of f of t by your f of omega, or this one here, this cursive f of t. So either this one or this one is your Fourier transform representation. The first property is in the differentiation. So your f of f prime of t is equal to your I omega times the Fourier transform. This may be extended to higher derivatives so that your f of f double prime t is equal to I omega f of f prime of t, which is equal to negative omega squared times the Fourier transform, and so on. For the integration of your Fourier transform of the integral of f s ds, is equal to 1 over I omega for times your Fourier transform plus your 2 pi c uh, times your Dirac delta function, where the term 2 pi c Dirac delta omega represents the Fourier transform, the constant of integration associated with the indefinite integral. And you also have the properties for your scaling, where your f of 80 is equal to 1 over a times the Fourier transform of omega over a. And then you have Fourier translation, where your Fourier transform of your f of t plus a is equal to e I a omega times the Fourier transform of your f of t. And then lastly, you have the exponential multiplication, where the Fourier transform of e alpha t f of t is equal to the Fourier transform of omega plus I alpha, where alpha may be real, imaginary, or complex. So that ends our topic on your Fourier transforms. In connection to this video, I have also sent you videos on the applications of your Fourier transform, which are also interesting to look at. So thank you for listening.